Okay, hello. I guess I'm the president, and I wanted to welcome you all here for this thesis defense of Luis Antonio Benítez. The title of this thesis is Spin Orbit Coupling in Graphene Transition Metal Dichalcogenide Device Heterostructures. And I know very much about his work, his very groundbreaking work on the definitive studies of and that really illustrate proximity spin orbit coupling in these structures and spin Hall effect and spin galvanic effects. I've been very, very impressed by the work that he's done. And so the format of this defense, there will be a presentation of approximately 50 minutes. After that will be a question and answer session with questions from dissertation committee, and then also by any members, attendees with PhD. So with that, I would like to give the floor to Luis Antonio Benítez for the presentation.
Thank you. So let me. Está compartiendo ya. Mal. Okay, so perfect. So good morning in America and good afternoon here. My name is Antonio, and I'm here today to defend my PhD thesis in physics. So the title of my thesis is Spin Orbit Coupling in Graphene Transition Metal Dichalcogenide Devices. And this thesis was supervised by Professor Sergio Valenzuela and co-supervised by Dr. Marius Costache and Professor Stephan Roche. So the work has been carried out in the group of physics and engineering of nanodevices here in the ICN2. So this is the outline of my presentation. I will start expressing what's the motivation and what are the research questions that I pretend to answer in with this work. And then I will move to present some theoretical concepts that will be discussed during this talk. And then our experimental approach. And then I will move to present the results and conclusion regarding a set of two key experiments, which are the spin orbit induced spin lifetime anisotropy and spin orbit induced spin to charge interconversion. Finally, I will. It's not sharing the screen. Oh, I'm sorry. So sorry about that. So this is the outline of my presentation. I will start with the motivation and what are the research questions that I pretend to answer. And then I will present some theoretical concepts that will be needed in this talk. And then I will move to the methodology. Here I will present my experimental approach. And then I will present the results and conclusion regarding a set of two key experiments regarding the spin orbit induced spin lifetime anisotropy and spin orbit induced spin to charge interconversion. Finally, I will recap the conclusions and present an outlook. So starting with the motivation and research question, this work is in the field of spintronics. You know that conventional electronics deal with the charge of the electron to store information or to process information, where in spintronics we aim to control the spin degree of freedom of the electrons. And the field is always seeking for creating novel materials and devices whose properties are influenced by spin polarized currents. And the foundation of the field dates back to 1989, where Albert Ferra and Peter Grumber independently discovered the GMR, which stands for giant magnetic resistance. And because of the enormous impact of GMR, they were awarded the Nobel Prize in 2007. So spintronics moved quickly from fundamental studies to real device applications. Probably the most famous one is in the field of data storage, where we use tiny spintronic device, for example, to read out information that is encoded in little magnetic domains in our conventional hard disk drives. But we still lack of logic devices based on spin manipulation. So now, this requires many ingredients, but particularly these two. First is to have good spin transport because we want to encode information in the spins. And then the spin orbit coupling, because this is going to be a tool for us to control the spins moving in a material. So in this context, since the first experimental demonstration of spin injection and detection in graphene, this material attracts the attention within the field. And this is because it's a peculiar properties. Graphene is a perfect 2D material with that is exactly one atom thick. So basically, it's all surface. Because of that, we have gate tunable electronics properties, high carrier mobilities, and very important for spintronics is that it has low spin-orbit coupling. So this is an advantage for transporting spins. That means the spins can propagate over long distances, but at the same time, it's a disadvantage because we have an elusive control of the spins. So now the question is, can we enhance somehow the spin-orbit coupling in graphene? And the answer to that is that we have different approaches, but probably the most promising one is the proximity effect. So the idea is that approximatized material acquires properties from its neighbors. For example, this layer B acquires properties from A and C. It's like resulting in a new material that has a combination of the properties of A, C, and B. Probably the most well-known example is in the case of having a superconductor and a normal metal, and the superconducting state extends to the normal metal in a certain length. When we go to atomically thin materials, these proximity effects can strongly modify these properties, and this is because they are entirely, basically all surface, so they are very surface sensitive. And the family of 2D materials is very large and is growing very fast. And among all the 2D materials, I'm interested in graphene and the semiconducting TMDCs. So the semiconducting TMDCs, because they possess a large spin-orbit coupling. So the idea is to combine them into heterostructures so we take advantage of the nice spin properties of graphene and the spin-orbit coupling coming from the TMDC. So this is not new. People have already studied this, and there have been some seminal works from a theoretical point of view and experimental point of view. But the nice thing about it is that the linear graphene bands lie in the middle, in principle, of the gap of the TMDC. So the transport is confined to the graphene, okay? So at the moment I started my PhD, there were still some open questions within the field, and some of them became my research question. So particularly these three. So first is, can we have experimental proof of the spin-orbit coupling acting on the TMDC in proximity, acting on graphene in proximity to a TMDC? And how is the spin dynamics in graphene modified by an enhanced spin-orbit coupling? And if we have a spin-orbit coupling in graphene, can we generate spin currents and demonstrate it? So answering this question will not only have an impact in the understanding the physics underpinning the spin-orbit coupling in 2D materials, but also will be a platform, for example, to design spin logic devices for information processing. So this is the thesis approach. I want to study proximity-induced spin-orbit coupling, and these are the two key experiments in my thesis. So the first is the spin relaxation anisotropy. This is a set of experiments. And second, the spin-to-charge interconversion. But before presenting the results and the details of these experiments, let me go to some theoretical concepts, starting with the concept of spin-orbit coupling. So this is the equation. Well, spin-orbit coupling is a relativistic effect, and this is normally the equation that we use in atoms. So here, the momentum of an electron is coupled with the spin. What happens is that an electron moving in an electric field, in the reference frame of the electron, that electric field is Lorentz transformed into a magnetic field, and that is felt by the electron, and then it acts on the spin. So then when we move to solids, the equation is similar. Here we have the momentum of the electron inside the lattice. Here is the spin, and here this plays the role of the electric field. So this particular spin-orbit coupling is the Roche spin-orbit coupling for two-dimensional electron gases. And it appears when we have broken inversion symmetry. In general, the spin-orbit coupling terms appear when we have broken symmetries. But I want to point out here is that we can always see these spin-orbit coupling terms as an effective magnetic field acting on the electrons. And it has two important consequences. That it lifts the spin degeneracy and induces spin precession. And I would like you to keep in mind this. And now I will move to say some words about the electronic properties of graphene. So graphene is a perfect 2D material made of carbon atoms that are arranged in this honeycomb type of structure. So these are the band diagram of graphene. Has two branches that touch at the K point. If we make a zoom near the K point, we have the energy dispersion goes linear with the momentum. And this is the electronic wave function that describes the electron in graphene. It has two components, one for each sublattice. And the nice properties, the electronic properties of graphene are well described with this Hamiltonian, where these sigma are the Pauli matrices describing the pseudo-spin. Now the TMDCs, the general formula is one transition metal and two chalcogen atoms. And from the top, they look like graphene, but they are 3 atoms thick. And this is how the band structure looks like. So we have in the K point and the K prime point. This is a semiconducting material. This is the orbital gap here. And we have a big spin orbit splitting that is reversed in the K prime point. And the electronic properties are well described with this Hamiltonian. So here we have this orbital part. This term tells us that we have this gap, the semiconducting gap. And this is the spin orbit coupling term that lifts the spin degeneracy. And this spin orbit coupling couples the real spin with the pseudo spin and the real spin with the Valley. And this is called the Valley-Zeeman. And now when we put graphene and TMDC together, we know that in principle, the linear bands of graphene lie in the gap of the TMDC. But if we make a zoom of these linear bands, we have a modified graphene band structure. And this modified graphene band structure is well understood using this Hamiltonian. So again, this is the orbital part. This is the linear energy dispersion of graphene. This describes the gap here that we have. This is the in-plane spin texture. This is the Rashba spin orbit coupling in this case that couples the spin with the pseudo spin. And this is the imprinted spin Valley locking that couples the real spin with the Valley index. And it's the Valley-Zeeman spin orbit coupling. So as I mentioned before, all these terms, the spin orbit coupling terms, can be seen as effective magnetic fields acting on the electron. So this is a schematic of the magnetic fields acting on the electron. So for the K Valley, we have the Valley-Zeeman effective magnetic field that is pointing upwards. And we have an in-plane, which is the Rashba effective field. And in the K prime Valley, we have the Valley-Zeeman is pointing downwards. Now, because this is effective magnetic fields induces spin precession, and they have different orientation and different intensities, one would expect that the spin relaxation for the spins pointing in plane and out of plane will be different, leading to an anisotropic spin relaxation. So this is one of the consequences of the spin orbit coupling that we want to address experimentally. So now another consequence is the spin to charge interconversion. So the idea is we pass a current, and this current is spin polarized. And the spin is spin polarized by two effects. One is the spin Hall effect, and one is the inverse spin galvanic effect, or Rashba-Edelstein effect. So in the case of the spin galvanic spin Hall effect, we send a current, and this current generates a spin current. And this is because the up and down electrons move in opposite direction towards the edge of the device. And the origin of this effect could be extrinsic, intrinsic, or a combination of both. So in the case of extrinsic spin Hall effect, it's because the scattering angles of the electrons depends on the spin orientation. And in the case of extrinsic, the spin Hall effect is driven entirely by the band structure of the system, particularly by this term, which is the Berry curvature. And normally, the intrinsic Hall effect is compared with the Magnus effect that is acting on a spinning ball flying in air, for example, that this ball experiences a force that makes and that causes a deviation of this of the original trajectory. Now, the inverse spin galvanic effect, in the inverse spin galvanic effect, we generate a spin density from an electrical current, okay? And the idea is the following. So we apply an electric field, and this electric field will shift the Fermi contours, okay? And because of the well-defined spin texture with the momentum, we end up with different number of electrons pointing in X and minus X. And because these Fermi contours have different size, we end up having a net spin density. In the case of the reciprocal, we generate an electrical current from a spin density. So this is a recap. the spin orbit coupling can induce anisotropic spin relaxation and the spin to charge interconversion. Okay, now I go to our experimental approach. So if we look in literature, there have been different ways to access to the spin orbit coupling. For example, we can measure the weak anti-localization measurements. We can do weak anti-localization measurements, and those measurements give us a direct proof of the spin orbit coupling in the system. However, they are restricted to low temperatures. And we are interested in measure these effects at room temperature. So this is more appealing, for example, if we want to go to application. Another example is, another method is this H-bar geometry. So the idea here is to apply a current between 2 and 3, and this current will generate a non-local voltage between 5 and 4 because of the spin Hall effect. But follow-up studies, so the nice things about this experiment is that there's no temperature restriction, but follow-up studies demonstrated that in this type of geometry, we can have multiple origins for the signal that we pick up. So this makes this method sort of improper to unambiguously detect the spin Hall effect. So this is the method that we're going to use, is the lateral spin valves. So the idea here is inject spins into graphene, and those spins will be sensitive to the spin orbit coupling in the material. So the nice things about this method is that we don't have a temperature restriction. It gives a direct proof of the spin orbit coupling and gives information about the spin orbit fields. So the basic idea of a spin valve consists of 4 electrodes contacting the graphene. And the 2 outer electrodes are metallic contacts, and the 2 inner electrodes are ferromagnetic materials. So the idea of the method is inject a current between the cobalt and graphene, and that will generate a spin accumulation underneath the contact, and that spin accumulation will diffuse toward our detector as a spin current. Okay, this is the substrate of our spin valves, and we use the doped silicon to globally backgate the device. And normally between the ferromagnet and the graphene, we deposit a thin oxide barrier that acts as a tunnel barrier for our spins. And this is a schematic of the spin chemical potential in the channel. So at 0, we have our injector, and our detector is at a distance L. And by measuring here, by probing the non-local voltage here, we can access to this spin chemical potential. And this measurement is non-local in the sense that the voltage that we measure is out of the current loop. And the non-local voltage that we measure divided by the injected current is what we call non-local resistance. So it's an important concept. This is the spin diffusion equation that tells us how is the spin chemical potential, how is the profile of the spin chemical potential in the channel. And here enter the spin relaxation length. That is a typical length in which the spin accumulation can be sustained. And it couples the spin relaxation time, which is again a characteristic time in which this spin relaxation is sustained. And this is a typical spin valve signal. So this is the data. The idea of this measurement is to measure the non-local resistance in the parallel and parallel configuration of our injector and detector. And for that, we apply a magnetic field which is parallel to the long axis of the ferromagnet. So in the case of having parallel configuration of the injector and detector, we basically measure a positive signal. And when one of the magnetization of our detectors or detector or injector the switches, we measure a negative signal. And the difference between these two values is what we call the spin signal, which is proportional to the spin accumulation. So a very important measurement now to really confirm that this is spin related is the spin precession measurements. So it's important because it gives us a direct confirmation that the signal comes from the spin, and we can extract from these measurements spin parameters, and this is going to be a way to obtain information about the spin orbit couplings. So typically, the typical spin precession measurements consist on applying a magnetic field which is pointing out of plane, and this will induce in-plane spin precession as the spins are moved from the injection to the detection point. So this is how the typical data looks like. It's also called Hanle measurements. So the idea is that we have a maximum at 0 magnetic field because all the spins that are reaching the detector are parallel, but as soon as we apply a magnetic field, these spins start to precess, and we detect only the spin component that is parallel to the magnetization of our ferromagnet. This is for the parallel configuration of the injector and detector, and we can do this for the anti-parallel configuration, and this is how the data looks like. And from fitting these measurements using this equation, we can extract very important speed parameters such as the spin diffusion coefficient and the spin relaxation time. Okay, now I go to how I fabricate the devices. So starting with the fabrication of the heterostructure. So I basically use this dry viscoelastic method. So I exfoliate the TMDC on a viscoelastic material. Then I look for the flake that I was interested to transfer. Then I just turn upside down my stamp, and then I align with my target substrate, and then I press it, and then I peel it off slowly. And for that, I use a microscope that help me to align everything at this micrometer transfer stage. And this is a typical picture of the device. So here we have the graphene, and this is the TMDC. And to fabricate the contacts, I use e-beam lithography. And to deposit the materials, I use e-beam physical vapor deposition. To characterize, I use Raman and AFM. Okay, now let's go to the results regarding the spin orbit induced spin lifetime anisotropy. So first thing that I did is to characterize electrically the TMDC. So for that, I apply a bias voltage and I measure the current. And this is a typical IDS for different baggage values. So I focus on this region mainly where the TMDC is not conductive. So I'm sure that I'm in the gap of the TMDC. So below this threshold voltage. So this is a typical picture of the device. So what is important here is that in the same device, we have a reference sample that consists of graphene channel, and here we have the heterostructure. So the idea is to compare what happened to the spins that move in the reference in pristine graphene and what happened to the spins that move in this modified region. So we start doing looking at the reference device. We did the spin precession measurements. So I applied the magnetic field out of plane. This is the typical how the typical curve looks like. And from this measurement, I can extract the in-plane spin relaxation time. Now I can apply the magnetic field also in plane and perpendicular to the long axis of the ferromagnet. So in this case, the spins will rotate in plane and out of plane. So the measurement will be sensitive to the in plane and out of plane spin relaxation time. And comparing these two curves, the almost perfect overlap between them qualitatively indicates that there's no difference in terms of spin relaxation time for spins pointing in plane and out of plane. That means in the reference device, we have isotropic spin relaxation. Now I move to the modified graphene region. And the first thing that we notice is that these two curves do not overlap anymore. So I repeat the same measurements, magnetic field out of plane, magnetic field in plane. So with magnetic field is out of plane, we still observe some spin precession. However, the signal has dropped close to 2 orders of magnitude compared to the reference device. Now, when the magnetic field is in plane, the response is completely different. Okay, so we have a zero signal, close to zero signal here at zero magnetic field, then it starts to increase until reaching a maximum. And in fact, this maximum is reached when the spins that are reaching this region are pointing out of plane. So this is a clear indication that we have an isotropic spin relaxation. Now we want to quantify this value. And for that, I use this method that was proposed in the group. So the idea is simple. We apply a magnetic field with a certain angle, and this will cause an oblique spin precession. Okay, so this is our spins. If we project these spins over the magnetic field and perpendicular to the magnetic field, this is kind of having a rotated reference frame, right? So in that reference frame, this magnetic field will not induce spin precession to these spin components, but will induce spin precession to these spin components. So if the magnetic field grows larger, eventually these spins will dephase. And the only contribution to the signal will be coming from these spins that point along the magnetic field. Now, if we project those spins on our detector, we have that the signal that we pick up will be proportional to a certain function that captures all the dynamics here in the system and takes information about the spin relaxation time for spins pointing in plane and out of plane, cosine squared of the applied angle. So these are the results. Here I'm showing the non-local resistance that we measure, which is normalized as a function of the cosine square for different angles. And this gamma here accounts for little tilting in the magnetization of our injector and detector. So in this line here, I'm showing my theoretical prediction of what would be the response in the case of having this anisotropic spin relaxation equal 1. And these are the experimental points, these dots, these open circles here, corresponding to the reference device. So we see that in the reference device, these circles nicely lie around this straight line, corresponding to the isotropic spin relaxation. Now, when we move to the graphene-TMDC region, the situation changes completely. So these points are very far from the line. And again, I can do the modeling to this and extract the spin relaxation, this factor, which in this case is close to 10 with a spin relaxation time of spins pointing in plane of 3 picoseconds, and for the spins pointing out of plane of the order of 30 picoseconds. Okay, now the question is why we have this. So for that, I'm showing here a schematic representation of the effective magnetic fields acting on the electron that moves in the K valley with a momentum K. So let's pay attention to this valley sigma effective field that is pointing upwards. So this will induce in-plane spin precession. So this will basically kill the in-plane spins. Now this electron can scatter, so we can expect that this spin relaxation time will depend on the intra-valley scattering. But this electron can also scatter to the other valley. In this valley, the valley sigma effective field is pointing downwards. So what this intervalley scattering is doing is creating an upwards and downwards fluctuating magnetic field that is killing the in-plane spins. Okay, so this recalls me the electron spin resonance technique, in which we use a modulating magnetic field, relatively small, that efficiently can rotate the spin orientation. Okay, in this case, in this technique, this magnetic field has to be in resonance to be efficient. Here, the situation is different because this is kind of diffusive process. But again, this intervalley scattering doing is kind of creating a fluctuating upwards and downwards magnetic field. So our colleague here in the ICN2 developed a method to study these systems. And what he found is that in the limit of having strong intervalley scattering, the out-of-plane spin relaxation time is completely different from the in-plane spin relaxation time. And the in-plane spin relaxation time is very small. Whereas if we turn off the intervalley scattering, the out-of-plane spin relaxation time and the in-plane spin relaxation time is more or less the same. So our measurements agree with this model, and we can do this again for different gate values. And this is what I did. So here I'm showing the different measurements, and what this graph is showing is that we have a clear modulation of this curve shape. So becoming more pronounced at positive gates and less pronounced at negative gates. And doing the modeling again, we see that this anisotropic factor goes from 7 to 20, showing a strong modulation of the spin dynamics in graphene tungsten disulfide. Now with this, I would like to conclude these experiments, saying that if we remember that what were my initial research question, the first two were, can we have a proof of the spin-orbit coupling and how the spin-orbit coupling affects the spin dynamics? Well, we know that that proof is the spin relaxation anisotropy, and how the spin dynamics is affected is affected in the way that the in-plane spins relax much faster than the out-of-plane spins. The in-plane spin relaxation is mediated by the interval scattering, and we can electrically modulate the spin dynamics in graphene tungsten disulfide systems. So this is acting kind of a spin filtering effect with a transmission that depends on the initial spin orientation. Now I go to the second results and conclusions regarding the spin orbit induced spin to charge interconversion. So remember, when we apply an electric field, we generate out-of-plane spins because of the spin Hall effect and in-plane spins because of the inverse spin galvanic effect. So we did a device which is similar to the previous one, but here we have replaced one of the ferromagnet by this TMDC, okay? So the idea is use this part as an injector or detector for the spins. So if we apply an electric field or electrical current between electron 1 and electron 2, it will generate an electric field and therefore out-of-plane spins and in-plane spins. And this spin information will diffuse toward my detector. But notice that the generated spins are pointing orthogonal to the magnetization of the detector. So in principle, we shouldn't measure any signal. But the solution is easy because we can apply a magnetic field in the Z direction, and this will not affect these red spins, but will cause a spin precession to these blue spins. So what we should observe is a spin precession response when we apply the magnetic field. Now, if we apply the magnetic field in the X direction, we don't change these blue spins, but we induce spin precession to these red spins. So again, in this situation, we should also observe spin relaxation, a modulation of the signal with the magnetic field. So notice that just by changing the direction of the magnetic field in the Z or X direction, we can prove either the spin Hall effect or the spin galvanic effect. And this is what we did. But before, it's important for us to electrically characterize the TMDC because the current that we inject can go through the TMDC and contribute to the signal. So we focus mainly on this region where the TMDC is not conductive, so below this threshold voltage. And this is the electrical characterization of our graphene underneath the TMDC. So notice that we have kind of a wide range of electron and hole conduction in this device. So we started studying the inverse spin Hall effect. So we're using this as an injector and this as a detector. And we are applying the magnetic field in the X direction, and this is the spin precession. So this is the result. So we clearly see a spin modulation of the signal with the magnetic field, and the fact that the signal is reversed when we switch the magnetization of our injector, it confirms that this is spin related. Now we can subtract these two curves, and here these are these red dots here, and here it's easy to see that at zero magnetic field, the signal is close to zero as we were expecting, and then the signal starts to increase because the spin precession, and then it goes to zero again. And this line here, the solid line, is our theoretical model that the only adjustable parameter that enters to the model is this spin Hall angle, which tells what's the efficiency of this effect. So from the injected spin current, how much charge current do we get? And we calculated that it's around 0.3%. Again, these measurements are taken at room temperature. Probably I forgot to mention in the previous results, all the measurements that I present so far are at room temperature. Okay, so now we multiply the spin Hall angle times the spin relaxation length out of plane, and we can compare with the existing values in the literature. For example, for the platinum or for tungsten, which are common materials used for this kind of effect. And we have that our work or this thesis present 1 order of magnitude bigger in terms of efficiency. Now we apply the magnetic field in the Z direction. So we induce spin precession to these blue spins. So we are probing the spin galvanic effect, and this is the result. So again, we see a nice spin precession, and the fact that the signal is reversed when we switch the magnetization of our injector confirms that this is spin related. Now we subtract these two curves, and this is the result. Here again, we have a zero magnetic field. The signal is zero, as we were expecting, and then it starts to increase because of the precession, and then goes to zero again. And this is the model that I did. And again, the only fitting parameter that enters into the model is the efficiency that I calculated to be 0.1%. Now to compare, I also multiply by the spin relaxation length. And this is the result, which compares well with the obtained in literature. Okay, now we want to study this as a function of the gate, but particularly the amplitude of this signal, which is proportional to the efficiency of these effects. And this is what we did for the spin Hall effect, which are these red dots here, and for the spin galvanic effect, these blue dots. So the first thing that we see is that we have a clear modulation of these effects with the gate, with the applied gate. And we have different gate dependence for the spin Hall effect and for the spin galvanic effect, whereas in this in the spin Hall effect, the signal is peaking around the charge neutrality point. This is zero, and in the case of the spin galvanic effect, we have a sign change for Hall and electrons. But there were some theoretical works that predicted that in the case of having intrinsic spin Hall effect, we should also observe a sign change in the spin Hall angle. So we thought, okay, maybe it's because of temperature broadening that we don't see this. So let's study this as a function of the temperature. And this is the result. So this is the spin Hall effect as a function of different temperatures and the carrier density. And at 200 Kelvin, we started to see some asymmetries between electrons and holes, and those asymmetries became clear at 100 Kelvin, indicating a sign change in this spin Hall angle. And our colleagues here in the institute calculate the spin Hall conductivity as a function of the temperature as well. And what we observe is that those calculations are our results qualitatively match very nice. And these are the parameters that they used, and they are very close with the obtained in DFT. Well, it's a factor of 2, the parameters that they use. But again, this tells us more or less what is the energy scales in our systems. I want to say also here that in these devices, we also observe an isotropic spin relaxation. Okay, now the conclusion of these experiments. We have a clear demonstration of the spin Hall effect and the spin galvanic effect in graphene with an enhanced spin orbit coupling. And this product is the largest reported value for any material to the date. Well, at least at the moment that we publicate this, we have a clear observation of the spin Hall effect and the spin galvanic effect tunability in the same device. And immediate application would be study this if we can use these spin currents to control the magnetization of a ferromagnet, for example. Okay, now finally I will recap the conclusions and present the outlook. So regarding the first set of experiments about spin lifetime anisotropy, the conclusions are the demonstration of anisotropic spin relaxation in graphene tungsten TMDC van der Waals heterostructures at room temperature, the observation of a fast in-plane spin relaxation, which is in the order of a few picoseconds, and such an efficient in-plane spin relaxation is presumably mediated by intervalley scattering, and the observation of electrical tunability of the anisotropic spin relaxation in graphene tungsten disulfide heterostructure. Now, our work partially agree with the existing models. However, in certain limits, we have some discrepancy. For example, when we go to large carrier densities of holes, we observe that this factor goes small in our measurements, whereas in the models, this factor grows larger in the same kind of systems. So the question is, are we changing this parameter? Is this Valley-Seaman energy gate dependent, or is it because we are only changing the rush by spin orbit coupling? Or somehow can we, are we modulating this intervalley scattering with the gate? And some possible study that can help would be repeat these measurements in cleaner devices. with higher mobility, for example. And very important is to control the twist angle. So far we cannot control the twist angle, but this definitely will be an extra tool to study, and to study the same measurements with different TMDCs definitely will help. Now the conclusions regarding the spin-to-charge interconversion experiments are the design of device that allow the separation of the spin Hall effect and the spin galvanic effect in graphene tungsten disulfide, the first time demonstration of simultaneous room temperature spin Hall effect and spin galvanic effect induced in graphene by proximity to a tungsten disulfide, the observation of a remarkable tunability of the spin Hall effect and the spin galvanic effect in magnitude and sign, and the demonstration of the spin-to-charge interconversion coexist with large spin anisotropy. So now the immediate question is, can we somehow enhance these efficiencies? But probably to answer that question, we should answer these two first. That is, how relevant is the interval scattering to reduce the spin Hall effect? And how much intrinsic and how much extrinsic spin Hall effect do we have? So some possible studies will be, as the previous case, linear devices will help control the twisted angle, different TMDCs. So probably, basically the same studies that apply to the previous experiments will apply here. And this demonstrates these two effects are highly correlated. And okay, so finally, I would like to say that these effects have been also observed in different groups. For example, the group of Professor Felix Casanova and Professor Barbambes, demonstrating that these effects are robust. And this test is in numbers. So I published 3 papers as a first author, and 1 that is in preparation, 1 in Nature Physics, 1 in Nature Material, 1 in APL Materials. In collaboration with people in my group, I published 2 papers and 1 that is submitted. I also had the possibility to present 2 invited seminars, 1 invited talk, 5 oral presentations, and 2 poster contributions. So with this, I would like to thank all the people that contribute to this work, particularly to the people here in the ICN2, in the nanofabrication facilities, and also in the CNM, and particularly the people in my group and the group of the theoretical and computational nanoscience for the kind help and all the support. And thank you for your attention.
Okay, so I think now the president can step in and continue the.
Okay, so thank you very much. That was a very nice presentation. So Christoph, are we meeting separately before the questions, or did we go straight in?
We can go straight in for the questions. Yeah.
Okay, so we will have a question and answer session first with the panel. Anyone on the panel who would like to ask questions? I guess I will go last. I have several questions.
I can go first if you want.
Okay.
Okay. So, well, first of all, I want to congratulate both you and Sergio, Marius, and Stephan for this really nice work. Okay, you have made very significant advances in this thesis. You have shown that you have shown quite conclusively that there is this spin proximity effect. Also, seems like also you have found some material of a very strong effect for the spin to charge interconversion. Okay, and this shows both in the quality of the thesis itself, which is very high, and also the quality of the publications, which are, of course, these results have been published in very high impact journals. Okay, so again, my congratulations to you. And I also, well, congratulate you on the presentation itself, because the presentation was really clear and, well, understandable. Sometimes it's hard to imagine all the geometries that are involved in these effects, but yet with the presentation and also with the thesis, you managed to convey it very well. Okay?
Thank you.
So, okay, so, well, we have some questions, of course. So can you go to slide 27, please?
27.
27, yes. Yeah, I don't know if is the screen being shared? Yeah, share the screen. That's 27. Okay, maybe then can you move one up, one down? Yeah, 26. It was 26. Okay. So I see that these are the reference measurements.
That's correct. Yeah.
Okay. And now, while seeing the presentation, I was kind of surprised to see such a small lifetime for, well, in this case, it was isotropic.
Sure.
Such a small lifetime for such a small spin lifetime for graphene.
Mm-hmm.
We know that at least the spin diffusion length in graphene is very large. And in very clean samples, it's of the order of few microns even. Okay, so is this is it just because of the high velocity of the carriers, although the spin lifetime is a small multiplied by the velocity?
Well, no, in principle, no. This case is because for this particular sample, the mobility was not so good. So this is all on silicon oxide.
Yeah.
So we're limited for that as well.
Okay.
So yeah, but normally we can improve this a bit, but not that much in case of not changing the substrate or doing something different that really helps with the mobility or something like that.
So how much would that spin lifetime be for
it can
encapsulated?
Go, sure, yeah. It can go, for example, there are reports that go larger than 12 nanoseconds.
Okay, that makes.
So a spin relaxation length of 30 microns or something like this.
Okay.
Very, very large.
Yeah. Now, can you go to slide 42? And maybe if you, I don't know what it is supposed to be. Yeah, okay. Yeah, that's good enough. All right. Well, this is just to introduce. All the measurements have been done with tungsten disulfide, which seemed to be the material that yielded the largest effect.
Sure.
Okay. Also, in your thesis, you do show some preliminary measurements, I guess, with tungsten diselenide, if I remember correctly, and molybdenum disulfide. Is that?
Yeah.
Okay. I was puzzled to see that. Well, in fact, I was puzzled as to why isn't the effect larger in tungsten diselenide, because both of the atoms there are heavier. Mm-hmm. So I would expect a larger spin orbit effect from that material.
In tungsten diselenide.
In tungsten diselenide with respect to tungsten disulfide, and yet it's tungsten disulfide the one that is yielding a
That's correct. Effect. Okay. So, for example, for spin to charge interconversions. Some theoretical work have, doing these comparisons between TMDCs. Mm-hmm. But the idea here is that it's a play between the intrinsic spin Hall effect, intrinsic spin orbit coupling, and the Bally Zeeman. So it's kind of an interplay between them. So one maybe one can have more than the other one, but it's not so good for spin to charge interconversion.
Okay.
So I think this is more or less why. In principle, yeah. So more and more heavy, the heavier, the better. But yeah, those calculations show, for example, that for spin Hall measurements, the tungsten disulfide is the most promising.
Okay, so maybe the plot that I have in my mind from your thesis, it's referred to the interconversion. So so continuing on that then, did you try the anisotropy measurements on different materials?
Sure, yeah. In the thesis, here I didn't show, but in the thesis, I'm showing that we repeated for MOS2, and well, WS2, MOS2, and WSE2. Okay. So we did it for those three materials. And it has been reported, as I mentioned at the end, in MOSE2.
Yes, I remember that. Okay.
So yeah, so it has been.
As you say, maybe it's just a little interplay. Okay. Also, I was wondering, if you go to slide 45 or 47, 45, for example, okay, you say in your thesis that for bulk materials, so for platinum or tungsten, this spin Hall effect angle is not really an angle, but a length, or it has dimensions of length.
Oh, yes.
Maybe I got it wrong.
Yeah.
Because you're dividing a current density that, of course, in 3D is
Sure.
amps per square meter divided by
That's correct.
2D current, well, so line current density. That is okay. So it has. So I was wondering. Of course, you need to convert to the same unit in order to make the comparison.
Yeah.
And you multiply by the spin diffusion length.
Yes.
I didn't understand why you multiply by the spin diffusion length and not the sample thickness. Or
I see.
why did you choose that length and not a different length?
Okay, I see.
Or I think, yes, I would expect either sample thickness or the sample width, but some geometrical length as opposed to some intrinsic.
Okay, I see, I understand. Yeah, this maybe can be confusing because in our experiments, we are going from 2D to 2D, whereas in this, conventional experiments go from 3D to 2D.
Yes.
So yeah, we have, so let's see, for example, we come from 2D and we go 2D. But now let's imagine that, okay, so not only the spin current that is reaching the graphene-TMDC region contributes to the signal, only just a window of amplitude equal to the spin relaxation length.
Okay.
And this is all 2D. I mean, there's no thickness because it's only in the interface.
Yeah.
So imagine that if only this window contributes to the signal, if we divide this by this spin current by the spin relaxation length. So in this scenario, it's like having a ferromagnet, for example, injected spins, and that ferromagnet will have like a width of the spin relaxation length. So in this scenario, is we can think in like going from 3D to 2D. But yeah.
Okay, so I see that you have given some thought about that. Okay, good. Also, I was wondering, when you talk about the outlook in slide 52, okay, if I remember correctly, when you apply strain to graphene, okay, it can behave as a pseudo-magnetic field.
That's correct.
Which interacts with the pseudo spin, and
Sure.
therefore. So, do you think that applying a strain might be a way, to split the energies of the K and K prime points, and therefore alter those inter-valley scattering, and maybe would be a different way of studying, and maybe, altering this inter-valley.
I see. Well, definitely the strength will modify, will add more spin-orbit coupling terms in. But as far as I know, those are more or less similar to the Rashba spin-orbit coupling. So more or less they have the same dependence. So I don't know if we can control like in the K and K prime, let's say, lift this spin valley degeneracy or something. But that will definitely contribute with more spin-orbit couplings in the system.
Yeah, rather than more spin-orbit coupling, I was just shifting the relative energies between the K and the K prime.
Sure, yeah. I don't think that those those terms will, lift the valley degeneracy. Yeah, I don't. As far as I remember, yeah. So they have more or less the same dependence of the Rashba spin-orbit coupling. So.
Okay. So let me see. Yeah, a curiosity. Of course, you deposit these ferromagnetic contacts,
Yes.
Okay, and also you mentioned the Johnson and Silsby experiments,
Yes.
which were the pioneering experiments for these non-local measurements. Quite well, not in the early days, there was a discussion about whether the fringing fields from the ferromagnetic contacts might give rise, they called it local Hall effects or something like that.
Yes.
And that that might, I don't know, make your signal dirtier, or that would be difficult. Those fringing fields would make your signal difficult to interpret. I don't know what's the status of this, and if people now say, okay, have real, do you know about this? Can you comment on that?
Yeah, well, in the case of non-conventional spin valves, the fact that we use spin precession measurements, help us to get rid of possible artifacts.
Yes.
The fact that we see this spin and the oscillation response. In the case of a spin Hall effect and spin galvanic effect, if the ferromagnets are very close, let's say, that will also mimic a signal of spin Hall effect, spin galvanic effect. But in our devices, the ferromagnets are like 4 microns apart from the TMDC. So in that scenario, these straight fields, for example, are strongly reduced.
Yeah.
So yeah, I think so. Just the way to be sure that this is spin related is the spin precession measurements.
Okay, I agree. Okay. Also, yeah, I didn't write down what slide is it, but can you go to the slide where you have this figure?
I divide that picture in.
It's this is in the spin relaxation.
Yeah, I know, but which picture? Because it's
the one F.
Okay.
Yeah, this one. Yes. Do you have, just to go out of curiosity? So do you have any idea why there is the difference at the positive magnetic field but not the negative magnetic field?
Here in the red curve.
Yeah, the red versus blue.
Yeah, so this is because in this case we are applying the magnetic field in plane.
Yeah.
So we are rotating as well the magnetization of our injector and detector. And this can be non-collinear, let's say. They can rotate differently.
Yes.
So this is why we may have some asymmetries here. So it's because we are rotating as well the magnetization of our injector and detector.
Okay. All right. So I think, my last question then. If you go again in your thesis, I don't know if you showed this one here. Do you have your thesis at hand?
If you
I don't know if you have this one. When you
yes, I have, yes.
This one?
Yes, I have.
Okay. Yeah. Okay. Yeah. Here, I saw it.
This one.
Here. So this one. So that's for the interconversion experiment. And you do the reference test, and you see, okay, it's, the charge neutrality point is at negative gate bias. If I remember correctly, for the previous experiment, the charge neutrality point was somewhat positive.
Yes.
Are these the typical fluctuations that you would get from sample preparation, or are you aware that this sample had some different treatment that made it go from a slightly p-doped to a slightly n-doped, or vice versa?
So this doping, external doping, we cannot control. So basically, the process of fabrication is the same for all devices. But so this external doping varies. Like sometimes we have no doping and we have some positive and negative. But this we cannot control it, even though we do the same recipe all the time.
Okay, so it's just the natural fluctuation that comes from that. Okay, so I'm done with my questions. Thank you very much. And again, congratulations to all the supervisors, to you and the supervisors.
Are there other questions? questions from panelists. Would you like to go, Christoph?
Yeah, let me also start by thanking Antonio for this very nice presentation and very clear and well-motivated presentation of these interesting experiments. And I enjoyed very much reading your thesis, and it's always a good source of learning more. And so I certainly do have a few questions, and yeah, I would also like to start with a question which is more related now to transport. I mean, in your first experiments you presented today on the proximity-induced spin-orbit coupling, you made the argument that you don't measure any current through the tungsten disulfide as a criterion that you're not having, I mean, that charge transfer is not important for graphene to TMDC. I mean, how can you rule out that all what you measure here is actually the contact resistance between your metal and the TMDC?
Okay, so that's correct. So in this, we always use like graphene, let's say conducting. I don't know if you are seeing this in the screen here and the pointer. So we use one graphene contact and one metal contact. So it's true that we have a Schottky barrier between the TMDC and the metal. This Schottky barrier here is kind of reduced, but it's
this
true
was
that
the case for the first experiment.
Yeah, yes, it's the same. It's the same, but here I shows only the picture that I showed you was only schematic, in the sense that let me go to this. Okay. So the contact that we use is this M1 and the one in the TMDC.
Okay. So did you measure straight through? You have two contacts on the tungsten.
Yes, we did. Yes, we did as well.
But
Yeah.
did it look very different?
They don't look different, but we need large bias voltage. That's true. I mean, to see some current flowing.
Do you know which material, I mean, in order to reduce the Schottky barrier, which TMDC would be most suitable?
To reduce the Schottky barrier? Well, the semi-metallic ones, in principle, they should have a less Schottky barrier, a smaller one. But these semiconductings, I think more or less all are the same, in the sense that they are semiconducting and they have a large gap materials.
Yeah. So what is the quantity which really matters for this Schottky contact?
Well, the fact that this is metallic and this is semiconducting, this is creating somehow the Schottky barrier.
Yeah. I mean, it's more reg function differences which really matters.
Yeah.
So I mean, people are now at the level where they can really measure very clean transport. So do you know what strategies have been used in order to get around the Schottky barriers?
I'm not aware.
I mean, you mentioned it briefly already, but it goes in.
I'm not, to be honest, I'm not aware of that type of works.
But I mean, in principle, these are graphite electrodes which are heavily doped.
Yeah. For example, if we use like two graphite electrodes, it would be a nice way to get rid of the. That's true. That's true.
Okay, but I've now a question to the experiment you performed. I mean, let's stay on this slide. I mean, do you understand? I mean, from a theoretical point of view, it's pretty clear that you should get the largest signal out for 45 degrees. No? This is where you see most of the influence of bringing the spin out of plane. But now if you compare, and this should be actually at the maximum point of your blue solid line in this plot. But if you look at your experimental data, I mean, it looks like your maximum, and I think this is getting even more apparent if you look at your figure, what is it, figure 4.5 on page 66 of your thesis. I mean, there you see that you don't get the maximum non-local resistant 45 degrees, but rather for more than 60 degrees.
Yeah.
Can you explain why this is the case? So I would naively expect that 45 should be always the largest signal.
Yes, so this is something that the first thing that I noticed when I was doing the modeling, in the modeling, all the signals are around, the maximum signals are around 65 or something like this. But this is, the maximum really depends in this type of experiments is at which value of magnetic field we are measuring. So the maximum can go, let's say, towards, for example, in this graph, towards to 1 or closer to 0. If we measure, for example, our 100 millitesla or 150 or something like that. So in this scenario, it really depends what's the magnetic field that we're measuring.
I mean, if I look at the panel 4, I mean, a figure of 4.5 panel A, I mean, it really looks constant, no?
Sorry, what page?
It's page 66. If you look at panel A,
yes,
it really looks, I mean, constant.
That's correct. But yes, so this depends as well on the channel length. So
yeah, this is the next question. This is also a good question. So why does it depend? But I mean, but if you focus on this panel A, I mean, it's pretty obvious that the 63 degrees higher. So do you know the reason, or what is?
Well,
constant. So it seems to be, looks really systematic.
Yeah. So the point is that so the idea here is to have like the maximum out of plane spins. Let's say we need to get like out of plane spin population in order to have like maximum signal. So this is real. So the reason is, and I don't see now a clear like figure in my mind why this is happening at 65. But this is something that I observe in my calculations. So yeah, it's something with the spin dynamics in the system, but strongly depending on the length at which, let's say, the channel length and the magnetic field that we are measuring.
But I mean, okay, this is, I understand this correctly. Panel A and B, they differ between what you use for detection and for injection. So they change the symmetry of your channel lengths before or after you enter the region where you have the TMDC.
That's correct.
So what also I don't really understand is for the 90 degrees case, I mean, why is the signal so much different in these two cases?
Okay. So the idea is because we have, when we apply the magnetic field out of plane, it's like having two different channels. Okay. So for example, if we inject with this F2 here in the screen, so they will have all this length to process. Whereas if we inject with this one, they will have only this little length to process and reaching the TMDC.
Okay.
So that's the point.
Okay. Then, I mean, I guess for both measurements, if you go to 0 degree, then you should simply get straight lines. Is this correct? Or do you have the 0 degree?
0 degree, this is the spin bulb, yes. This is like the 0 degrees is like just a line, let's say a constant. But So I'm not presenting. I think I don't. Yeah, I don't presenting that measurements there. But yes, we measure like typical spin bar, for example, if we apply a magnetic field at 0 degrees.
Okay. Okay, but then I have one more short question to this experiment, because I just, now this is more curiosity, but if you go to the page, just figure 4.4, where you show, in particular in the graphene on silicon oxide samples, if you look at the 90 degrees trace, I mean, this is just handling. So my question there is, why does this trace not go to 0 for high magnetic fields?
So you are looking at page 64?
64 and then figure 4.4, panel A.
Okay.
If you look at the 90 degrees trace, the black one.
All right.
So this should be its standard handler, no?
Yes.
So I wonder why should, I mean, it's for high B fields, this line should go to 0.
Not necessarily
about the background in this. And I mean, I think it's important, the background, because that's something which goes directly into the way how you calculate then the anisotropic.
Yes. So at 90 degrees, if the magnetic field is large, so we are tilting the magnetization of our injector and detector as well in the direction of the magnetic field. So the signal starts to increase again. So there's a region that the signal is 0, let's say, but then it starts to increase again. In this case, the magnetic field is not that large, but the signal starts to increase. I mean, it's not completely 0. There's 0 in like a lower magnetic field, kind of 0.1 Tesla.
But is this really true? I mean, are you already at around, I don't know, I mean, 150 millitesla, you're starting already to tilt?
No. I mean, we're starting, no.
The electrodes out of plane?
No. It's just, in this case, so at these magnetic fields, we are, I mean, the tilting angle is very small. So, but here is like.
Let's talk about the 90 degrees trace. Okay.
Yeah, sure. So at 90 degrees is applying the magnetic field out of plane. So this is like typical Hanley measurement.
Exactly. I mean, for the graphene on HPN, I think everything is perfectly fine.
That's correct.
I
but
mean,
the point here,
you go to 0, but I mean, for the silicon oxide, I'm just worrying that there looks like that the background signal. That's
correct. So in this case, I have also a little background here. That's why it's not remove the background. So that's why we also have this offset that prevents us to see this going to 0. So this is just raw data.
Yes, but I think it should also be in raw data that it goes to 0, right?
If you have a background that is not spin related, not necessarily.
Okay, so you say that this really, okay, but then it should be length dependent, or, but I mean,
so sorry?
It should depend on the length. You could check this, no? I mean,
as well, yeah.
Okay. Anyway, let's go to more general questions. I mean, I think you really showed a very nice experiments where one sees the impact of the proximity-induced spin-orbit coupling. So my question is, what will be your next experiments you would like to do in order where you actually even enhance the spin-orbit coupling? So what would be a good strategy to follow to see even bigger effects of the spin-orbit?
Okay, so
the spin-orbit coupling mechanism.
So I think it would be nice to start by fabricating devices, silicon, I mean, graphene channels on top of HBM, but with mobility is really, I mean, they're really increasing the mobility, and see if that helps. Also changing the material, even though, for example, it had been measured in MOS2, but the values are smaller. So I will start by doing this. And we know that the twist angle is also very relevant. It would be nice to have a systematic way of controlling the twisted angle and find the right angle where the spin orbit couplings gives kind of the maximum efficiency for these effects.
So do you have any feeling how does the spin orbit coupling depend on twist angle? And what are the mechanisms which are relevant?
Yeah, there are some articles that say that, for example, the Rashba spin orbit coupling can be turned off and on and off just by changing the angle. So in that scenario, the spin galvanic effect shouldn't be present, for example. So I think it's relevant.
Okay, and this is there's a lot more to do. And
sure, yeah.
My very last question before I hand over to Roland is, so this is now, I mean, from your point of view, so now having done all these experiments, so what is your current level of understanding what is limiting the spin lifetime in graphene?
Well,
I mean, in these samples, but also in the HPN samples. And
well, we know like two important things that the initial prediction that the spin relaxation isotropy that should fall to 0.5 is not there. So we know that I mean, to be honest, we don't know that much. It's still an open question in the field. It's something to keep working on that. We know that it's possible, impurity stuff, magnetic impurity stuff that can be present in graphene. The spin entanglement. So there have been like many theories trying to explain why we get this, for example, anisotropy spin relaxation equal 1. But yeah, that's still an open question.
Okay, Roland.
Okay, I have a number of questions, but before I do want to say I really enjoyed your presentation, and I really like the quality of your work. So I wrote on the top, quality matters. So when I read your papers and see how the experiments are done, and they're done very well, it gives me some faith in the whole scientific system here, where where it's not just I'm not sure exactly how to put it, but there have been many claims of, for example, a spin Hall effect over the years and so forth.
Yeah.
In such systems. And then when I see, your work, I think, okay, I believe it. Things like this. Yeah, so I very much enjoy that aspect about your work.
Thank you.
So I had a number of questions. So one is, so you've done these 3 experiments, one on spin Hall effect and one on spin galvanic effect and one on the anisotropy. So can you get those spin orbit coupling constants like the Valley-Zeeman and Rashba? Can you extract those out from some combination of those experiments?
It's not so straightforward, I would say, and to get like spin orbit coupling energies from the measurements. What we know, for example, is from the calculations that I showed, is that they are more or less too close to the reported values in the FT, for example. But from the measurements, I don't see that this is straightforward to see. Maybe doing a simple model, a theoretical model that can allow us to get the spin orbit couplings from the measurements.
I know near the end you had an expression that had a ratio of coupling constants with some inter-valley scattering times and things like that. So I'm just wondering, like, what makes it difficult to extract out the parameters?
Oh, okay. So you say that from this anisotropic spin relaxation experiments, I'm showing.
Yeah. For example, you had like near the end, in conclusions, you had something with the inter-valley scattering time and so forth. Which
okay, so this is using this theory that was proposed by Aaron.
Exactly.
So we can assume these values and get what is this we can know from experiments. This we can assume. The problem is that these are unknown. These are unknown. So, but we can assume this from literature, and then we can extract this ratio here. But the point is that we cannot access to this one and this one independently, or this one independently.
But if you like, so I see the anisotropy, there's some ratios, but just from the other experiments, like the spin Hall effect and the spin galvanic effect, can you do some combination of results from the various experiments to try to isolate what is the Valley-Zeeman and what is the
okay?
Is there some strategy about that?
I think it's possible. We know, for example, I mean, it would be nice to have kind of the Rashba from these measurements, and we know more or less what's the Valley-Zeeman in our systems, but I think it's possible, yes. So I should think about it.
Okay, so I have another question that's like, I feel like I should understand this better, but it's always puzzled me a bit. And you do have a figure. So let me ask the question. So, you know, you talk about this band structure. There's two valleys. There's a K valley and there's a K prime valley.
Yes.
And you have a nice figure inside your thesis that shows, you know, the spin structure of these two valleys. And so I guess I have this question. Why do the effects in the K valley and the K prime valley not cancel? Like this is for the spin Hall effect and the spin galvanic effect. So I just want to understand how these two are related.
So this is a good question, because in the case of a spin Hall effect, and if it's driven by intrinsic spin Hall effect, so we have one very curvature in the K valley, and a negative one, a negative one in the K prime. So if there is mixing between these, in total it should be canceled out. So so this is one of the open questions that we don't really understand, because we measure this anisotropic spin relaxation. That means that we have intervalley scattering, but we also observe this nice K depends of the spin Hall effect, and these calculations are done only for one valley, so it's intrinsic. So maybe maybe because we are somehow. So my question is, can we have something like weighted intervalley scattering, and say that we have more intervalley scattering that goes more to one valley than the other valley? So then in that sense, we have like a difference between these two valleys, and that can produce a spin Hall effect. But in theory, this should be canceled out. But this is what we don't observe that.
Okay, so in your figure 4.1, so I don't know if you have this on hand, but you know, the out of plane components of spin look like they flip over when you go from K to K prime. And that, you know, that makes sense to me. But when you look at this, you know, in plane spin structure slightly away from the K point, you have this like Rashba type of. But then it's drawn, the in plane components in the K and the K prime look like they're in the same directions. And I'm just wondering, how to understand that.
So could you repeat me the question, please?
Like if you look at figure 4.1 on page 60, yes.
Oh yes.
Yeah. So there's a nice picture. Let's see.
Oh yes.
Figure. Yeah. So the in-plane components on the two valleys look like they're the same, essentially, right?
Yes. Yes.
And is there some understanding?
Okay.
Like
yes.
Yeah. Because those would give the same. Those would give the same, like, you know, you know, inverse spin galvanic effect. So if I could understand that,
that's correct,
spin structure, then it would you know, yeah, I would understand better about, you know,
Okay.
these two values.
So what I understand here is, for example, if we are in the K valley, we have the spins pointing in one direction,
Yeah.
and then the spin orbit coupling term preserves the time reversal symmetry. So if we go to the another valley, at that point, this spin should be pointing in the opposite direction.
Yeah.
So at the end, this is giving the same in-plane spin texture for the two valleys. I don't know if I'm clear.
In the last part, I didn't quite follow the very last part.
So the idea is, so let's imagine that we have. Okay, so I'm looking at the figure 4.1a.
Yeah.
So this we have like spin pointing, and so enter into the page.
Yeah.
And then if we, make this time reversal operation.
I see.
So this is pointing in the opposite direction in the other valley.
I see.
So at the end, the spin texture is the same.
Got it. Okay, so there's a spin and also a K inversion, I guess.
That's correct, yeah.
Okay, then so that's where the extra minus sign is. Okay, very good. Okay, I had another question, different question, is you have some data on gate dependence, and you talked about gate dependence, and most of the experiments, what's really nice about your experiments is that you work inside the gap of the TMD, right? What happens to these experiments if did you do experiments like not inside the gap, so you're have conduction inside the TMD? What happens to your results?
Okay, so we mainly focus on for this spin galvanic spin to charge interconversion. We mainly focus on the region that the TMDC is not conductive. So we didn't kind of measure the other side, but we tried like not systematically, and we didn't measure like any signal, but in principle the spins could enter to the TMDC and also contribute to the signal, but we don't have like systematic measurements on that. So in a particular device at very positive gates, we didn't observe like any signal. We didn't observe like any signal at very positive gates.
Oh, I mean, for the anisotropy, I guess you would have absorption or something. But for the spin Hall, for those or spin galvanic, you might expect just to see effects from the TMD itself, which has a lot of spin orbit coupling. So I wonder if any of these spin charge conversion experiments like showed anything.
Yeah. So that's the what I was trying to say. So for example, in our samples, in our devices, in our experiments, as you said, we focus on the region where the TMDC is not conductive, where we also try to measure like a high positive gates. But we didn't observe any signal. But in principle, the spin should be absorbed, no? Can be absorbed and enter to the TMDC and also contributes. But we don't have like a systematic measurements on when the TMDC is sort of conducting.
Do you know why? Is it just that the conductivity shorts out the signal or something? Do you have a sense about? I don't see anything.
I don't really know.
Okay.
Yeah. So there's still like work on that. So I don't have a clear answer on that region, let's say.
Okay. No problem. So the other data I really liked, sort of newer data on slide 38. This is the large anisotropy with, I guess this is related to intervalley scattering. Is that so? You're changing the gate voltage, and then I guess the claim is you're changing the intervalley scattering. And is this all within the non-conducting regime for the?
No. No, that's the issue. So in
Okay.
this particular measurements,
Good.
at positive gates, we observe like this signal, but at these gates, the TMDC is conducting
Oh,
somehow.
I see. I see. So
yeah. So in this case, like it's not only proximity effects. There can be, extra things happening in the TMDC. But this is what we observed.
I see.
But for the spin-to-charge interconversion measurements, we didn't kind of did systematic measure in the conduction of the TMDC, where the TMDC is conducting.
I see. So mixed inside here is somehow the lifetime anisotropy of the TMD.
That's correct. Yeah.
I see.
Yeah. So in this part is kind of like the TMDC bands are somehow playing a role, or not only the modified graphene bands.
I see. Very, very nice. And then, okay, let's see. There's, I guess, two. So, okay, so one thing I'm curious about is, in your spin Hall effect, you have this gate dependence, changing the carrier type. And so I guess that's some kind of signature of intrinsic effect.
Yes.
Do you have a sense about how much intrinsic versus extrinsic effect you have inside this?
Well, that's a good question, because this what we observe here is it corresponds well with the calculation that consider intrinsic spin Hall effect. But in the same device, we also observe anisotropic spin relaxation. So this is the complicated part.
I see. So, I mean, if it's anisotropic, then okay. So
then we have interbody scattering, which mixes the Berry phases, and then in principle, the intrinsic spin orbit coupling, the intrinsic spin Hall effect should just vanish.
I see. So it's complicated.
That's correct, yeah.
I see. Got it. Fair enough. Okay. And okay, so my last question, actually, I'm just kind of curious because there's a video that you showed with the basketball, Magnus Force.
Yes.
So I showed that same video in my class. This class is all consuming, and it's like a online, all online delivered class on mechanics. And this is about Bernoulli's law. Okay, so I was like, oh, I love this video. I found it, and I guess we were just both searching the internet and we found the same video. Mm-hmm. So how do you understand the connection of Magnus force and this like spin Hall effect? What's how closely is that connected actually?
Well, I would say that so kind of the bands are kind of the air where the spins are flowing, and the force is that is the feeling, the electron is feeling is because of the spin of this electron in that band. It has this very curvature. So it's kind of an analogous. It's not the right way to see it, but something like this.
It's fine. It's a cool video too. Okay, well that was my last question actually. So we can open this up to questions of anybody in the audience, virtual audience, who have PhD. So are there any questions from any of the participants with PhDs? Okay, if there is not, I guess the next step would be we would need to deliberate. Is that correct? Is that the next step?
Yes.
Okay. All right. Okay, hello. Yes, we have deliberated, discussed, and we've returned with a grade. And the grade that you have received is a pass with a grade of excelente. Congratulations. And then in terms of cum laude, this is something that you will learn the outcome of that secret vote within a week from now. So congratulations on passing.
Thank you. Thank you very much.
Defense with a grade of excellent.
On behalf of the committee, I will, so on behalf of both of you, I will congratulate Antonio. Okay, and yeah, so congratulations.
Thank you. Thank you.
Okay, so now we're done.
Do you want to say goodbye to people watching you from home?
Okay. Now thanks all for being here, and thank you to Roland and Christoph for accepting being part of this committee, and thanks to the people that is watching online. Yeah, for sure. That's it.
Okay.